Okay, folks, you at the back, please shut your laptops. Hello? Shut your laptops. All of you. That's the attendance. What about the rest of them? Okay, folks, so let's begin. It's, wait, 213 and 214. I think the first one is 213 and 214. This is if I'm correct. Is this right? Double check. Okay. All right, let's begin. So in the next series of lectures, we will look at the problem of how to train a neural network. Today's lecture will be describing the problem of learning. I will talk about the perceptron rule. I will briefly mention greedy solutions, but I won't actually go over them in class. They are on the slides, and they will turn up in the quiz. And we're going to begin the we'll introduce the notion of empirical risk minimization to train neural networks. So here's where we are. In the past couple of classes, wait, those are only 2 polls. What's the third? Okay, so we have 3 polls today. Anyway, in the past couple of classes, we've introduced what neural networks are. They are these layered compositions, networked compositions of really simple units, which together somehow manage to do a whole lot. So we saw that these networks are actually, they can model any Boolean function, which means that if you give me a Boolean function, I can design a network for it. They can model any classification boundary to arbitrary precision, meaning that if you give me a classification boundary, I can, in theory, construct a neural network that will approximate it with arbitrary precision. And so also, they can model any continuous valued function. Now, in each case, for the network to be able to perform these operations, it must have sufficient architecture, a sufficiently deep network where each of the layers is sufficiently wide and they are sufficiently connected. Now, given all of this, here's what we found. In all of these various AI tasks, the neural network is this magical box which takes an input and generates output. And so the box itself is a function. And of course, once we realize that this box is a function, then some questions pop up. We are speaking of mathematical objects. Whereas when I'm looking at this AI task, there's a game state going in and a game state coming out. These are not mathematical objects. So how do we convert these into the form that can actually be operated on by functions? And how do we actually compose a network that computes the appropriate function? So we have several questions to answer. First is, how do we represent the input and the output? The input and output must be mathematical objects. They must be numbers. They must be vectors. They can't, a game state is, we don't know what really a game state is, right? It has to be converted to something mathematically interpretable. And then the function, of course. We're going to look at how to specify the input and the output later in the course, in the next lecture. Today, we're going to focus on the problem of composing the network that performs the requisite function. Now, here's how we had defined the network. It was a network of very simple units, and the most basic unit was the perceptron. And can you close now? So the perceptron we saw was this unit which obtained a bunch of inputs. Corresponding to each input was some weight. So it considered the weighted sum of inputs and compared it to a threshold. And if it exceeded the threshold, it fired. That was the most simple version of the perceptron. If you take one step further, you can think of the perceptron as computing an affine function of the inputs. Again, to remind you, an affine function is the weighted sum of inputs plus a bias, and then applying some kind of an activation on these affine functions. The simplest activation was just the threshold function on top, but we could have other kinds of, once we decompose the operation of the perceptron in this manner, where you first compute an affine value and then put it through an activation, then the activation function itself can be anything. So I can also redraw the perceptron like so. Instead of having a weighted sum of inputs plus a bias, the bias can also be represented as just an additional input that's pegged to 1. And the weight of that input would be the bias. So very often in my pictures, I will not have an explicit bias of this kind. In this case, you must assume that there is a bias. It's just that one of the inputs has been pegged to 1, and its corresponding weight is the bias. Now, the activation functions can be anything. Again, as we've said, they can be threshold functions, they can be sigmoids, they can be other kinds of functions. It doesn't really matter. But this is it matters, but not for the purpose of understanding what the perceptron itself is. So this is the basic unit. But the function that we are actually computing is a network of such units. And we're going to assume that the network is a feed-forward network, which means that when you process any input, it means that the network is directed, and when we process any input, each neuron or each perceptron in the network sees that input only once. There are no loops. So the information flows from the input unidirectionally all the way to the output. Now, when we decide that this is what structure must be, then the questions that we must answer when we are speaking of designing the network are, the architecture itself, how many layers, how wide the layers are, and so on. For now, since we are speaking of approximating functions, I am going to assume that whatever network we have has an architecture that's capable of modeling the particular function that we are trying to model. Now, how that architecture is arrived at is something that we won't get into in today's lecture. That's a big heuristic problem. We're just going to assume that the network has sufficient architecture. And so now, okay. So now here's what the network is. It's got it's a layered composition of these basic units. Every one of these units has some weights and a bias. And so this entire network is a structure, mathematical structure that takes in some inputs and finally computes an output. And it has parameters, namely the weights and biases of the neurons in the network. So you can represent the entire network functionally in this form, f of x semicolon w. The semicolon, anything that follows the semicolon in this notation represents a parameter. Anything that comes before the semicolon represents an input. And so this is a parametric function with parameters w. The entire network is just a parametric function. So when we speak of learning a network, something that we will talk about more in detail today, we are really speaking of learning the parameters w, because we are assuming that the architecture of the network is given. And the question is, how do we set these parameters w for the network to do whatever it is you want it to do? So that's the setup. Any questions? None? Okay. So let me continue. We've seen in past classes that the multi-layer perceptron can represent anything. Guys, if you don't have your name tags, please make one, because I need to know who you are, right? So what this means is that regardless of the function you give me, I can always construct an MLP that computes this function. Since we are specifically assuming that the architecture of the network is given, what this means is that we can always choose a set of parameters W such that the network computes this function. But then, so this picture to the right represents a function. In this case, it's a two-dimensional input. The grid, the mesh represents the function. And I can always set the parameters of my network to the left, the parameters W, so that the network itself computes the function to the right. Now, how exactly do we construct this? I've given us a network. There's a function that it must compute. How do I set the parameters W of the network so that the network computes exactly this function and not something else? Now, for very simple functions like this one, where we have a diamond-shaped decision boundary, and we want the network to output a 1 inside and 0 outside, you can just handcraft the network. You can literally just set the parameters of the network to capture the different boundaries or the lot. We saw how to do this. Now, this is fine, but this only works for the most trivial of functions. When the functions get more complicated, you're not going to be able to handcraft your network parameters. So how do we actually design the network for more generic functions? How do we set up the values? So this is the situation we have. We have some function g of x, where x represents the input. We are given a network with appropriate architecture. And the question is, how do we derive the parameters W for the network such that this network computes the function on the right? Now, here's how I can visualize it. The function over here, so the figure to the right is showing a one-dimensional illustration where the input is one-dimensional. But you have to sort of generalize this and think of multidimensional inputs in your mind. So when I give you a function g of x, so if x is a scalar, then g of x is going to be some curve of this kind. Now the network itself is a parametric function with parameters w. And for any specific setting of w, so this would be my g of x, the network is going to compute some other function. This is my f of x semicolon w. And so when we are speaking of training the network, the question we are asking ourselves is, how do we set these parameters w such that the gap between the function that the network computes and your target function is minimized? In other words, how do you set the w such that this area is minimized? If that area goes to 0, then the network is computing your function. Make sense to everybody? Right. Any questions? Right. Now, in order for me to be able to specify this, I need to have a way of quantifying this area. In order to quantify the area, I first need to define an error, which quantifies the gap between what the network currently computes and what you want it to compute. So we need to define an error function, which I've just represented as error right now. And the shaded area, of course, is going to be the integral of this error over the entire input space. So it's going to be the integral of the error from over x going from minus infinity to plus infinity. And our problem is that of determining the w that minimizes this error. Now, what would be a problem? What could the problem with this very simplistic setup be? Anyone? Yeah.
Finding the error function.
I can define an error, right? The error has some properties. It has to be 0 if the two are the same and positive if they're not. Yes, Virginia?
You don't know what g of x is.
I don't know what g of x is, right? So the problem is, for this to work, g of x must be specified everywhere. And in practice, we don't know what g of x is. So what do? We're going to sample our function. Instead of knowing g of x everywhere, we're going to sample it. We're going to collect a bunch of x's, and at each x, we are going to get the corresponding g of x value. So we have a bunch of input-output pairs where you have the x and the corresponding g of x, You're basically reading the g of x off this mesh here. And so all you're left with is the set of input-output pairs. And from the set of input-output pairs, you will try to learn the function. So if you go back to our original picture, this is what we will have. Instead of having the function g of x everywhere and being able to quantify the shaded area, all we will have is a bunch of an empirical collection of inputs, x's, and the corresponding g's, which are the value of the function at these x's. And now your network is going to compute some other value at those inputs. And so instead of trying to minimize the entire shaded area, what we will do is to minimize the total length of these red lines. The error, the average error of the network over the collection of samples that we've got. Now, it's very easy to collect such samples. You're basically just going to be collecting input-output pairs for your data, like images and their captions, speech and its transcription. So sampling the function is very easy. So we can compute this function, compute this empirical estimate of the error, and then subsequently, we can try to estimate the parameters w that minimizes this empirical error. Now, will minimizing the empirical error necessarily also minimize the actual error between the network and the function you want? Yes or no?
Yes.
Yes, will it?
It's a fair assumption to make.
It's not a fair assumption to make. It's an assumption that we make, right? If I can set my W values to just minimize the length of those red lines, you're hoping that in so doing, it's going to actually minimize the shaded area. There is no guarantee that it will do this, right? So we're actually going to be minimizing the empirical error, but that's not what we really want to minimize. We want to minimize the total error, okay? And so here is what our problem collapsed to. We are given a collection of training samples, basically samples of the function g of x. We are computing the empirical error, which is the average error between the network and the actual function over this training collection. And we are going to try to find the function network parameters such that this average error is minimized. And we hope that if we do this right, that whatever function the network learns, or the network represents, is going to be true everywhere, meaning that the network parameters that we have determined to minimize the error between the network's output and the true output at these locations are such that the resulting function fits g of x everywhere. That's just a hope, but there's no guarantee. Questions? No? Okay. So the story so far, learning a neural network is the problem of determining the parameters of the network, the weights and the biases, that are required for it to model a desired function. And the network must have sufficient capacity, meaning sufficient width and sufficient depth, in order for the network to, in order for us to have a chance of actually learning a network that captures this function. We are assuming that it has sufficient capacity. So the problem of learning is simply that of determining its parameters such that this error is minimized. Now, ideally, you want to optimize the network to represent the desired function everywhere. But this requires knowing the function everywhere. So in practice, what we do is to draw input-output training instances. So these are what the training instances are. These are samples of your function. And we're going to estimate the network parameters to fit the input-output relation at these training instances. And we hope that when we do this, the resulting network fits the function g of x everywhere. Okay? So do you mind shutting your laptop back there? You. Yes. Thank you. So you have your first poll. That's 205 and 206. So is everybody done? Most of you are done. What's the answer to the first question? And the second? The first statement, is it true?
Yes.
Second? Third? And fourth? Right. So since neural networks are universal approximators, any network of any architecture can approximate any function. This is not true. We saw this in the last class. On the other hand, so what this means is that the network architecture must have sufficient capacity for it to model any given function. The network is actually a parametric function, where the parameters are the weights and biases. And these parameters must be learned for the network to best approximate the function. Even if the network doesn't have sufficient capacity, if the architecture of the network is insufficient, it can nevertheless be learned to approximate the target function as closely as it can given that architecture, which is why we are not going to explicitly delve into how to set the architecture. Now, the parameters, on the other hand, can obviously not be perfectly learned from just a few samples. In principle, or in reality, you'd need to know the function everywhere. We just don't know it, and so we're taking a guess from the few samples that we do have. So let's begin with a simple task. We're going to try to learn a classifier, which is simpler than learning regressions. This was amongst the earliest problems addressed using MLPs. And so that's what we will consider. Specifically, we're going to consider binary classification, but this generalizes to multi-class classification. Now, in binary classification, what is the desired output of the network? It's either 0 or 1. You have only two classes 0 and 1. So what would the error be? If the output of the network is the correct class, there is no error. If the output of the network is an incorrect class, there is an error. So here, if your target function is the one shown by the dotted line, now the output can only be 0 or 1, and I'm showing you one-dimensional input. The network function shown in green is going to come, for the wrong value of w, will compute incorrect outputs at a certain number of locations. And so the total error over here is going to be the number of instances on which the network has made an error. So it's going to count the number of orange bars. It's going to count the error is the number of training instances where the network output did not match the desired output. When I want to learn the classifier, what I'm really speaking of is learning these W's such that the count of these errors, shown here as a formula, is minimized. Now, let's start off by considering the original multilayer perceptron as defined by Rosenblatt. Now, in Rosenblatt's original model, the basic unit had a threshold activation. So each perceptron, each unit, computed an affine function of inputs and compared it to 0, compared this affine value to 0. If it was positive, it was greater than 0, the output was 1. If it was less, the output was 0. And our problem now is to train this network of such basic units using just some training data, collections of inputs and outputs. Now, the simplest multilayer perceptron over here. So this was what Rosenblatt's model looked like. Each of the units within the model was just this basic threshold unit. Now, what is the simplest such model? The simplest such model is just a single perceptron. Instead of a network of such perceptrons, I can just have one perceptron. So if I have just one single perceptron, then we know how it operates. A single perceptron compares the weighted sum of inputs to a threshold. If the input is greater than the threshold, the output is 1, otherwise it's 0. So the boundary between where the output is 1 and the output is 0 is where the weighted sum of inputs is exactly equal to the threshold. So what does that look like? What is the boundary over here? Anyone? The boundary is a hyperplane. The function is a Heaviside function, right? So you're basically speaking of the unit looks like so. You say summation wi xi greater than threshold. This is your question. And if it's greater, the output is 1. Otherwise, the output is 0. And the crossover happens where summation wi xi exactly equals t. So this is the equation for a hyperplane. And that's why the function looks like a Heaviside function. There's a hyperplane. All inputs on one side of the hyperplane are 0. And all inputs on the, result in an output that's 0. For all inputs on the other side of the hyperplane, the output is 1, right? Now, this is the function that we would like to learn if I'm just learning the simplest classifier, a network of just one unit. Except that we wouldn't be given the entire, so when I'm speaking of learning this function, what I'm really speaking of is learning the weights and the threshold. Except you're not really going to be given the entire function. All you would be given is a bunch of training samples of this kind, some collection of inputs where for some inputs the output is 0, and for other inputs the output is 1. So you just be given those colored dots, the red and blue dots, and from that you have to learn the entire Heaviside function. So this is the problem we have. We are given a bunch of training samples as shown over there. And from this training sample, we have to learn the Heaviside function. But what does this actually mean? We want to learn the hyperplane that separates the positives from the negatives. So in other words, we want to learn the equation for this boundary such that this boundary separates the positives from the negatives. So and the equation for the boundary is entirely specified by the weights and the threshold, right? And let's see how we can solve this. But before we do this, what kind of a function is this? When I actually learn this boundary over here, this has the structure, the boundary is summation I wi xi plus b equals 0, where b is minus t, right? What kind of a function is that? That's an affine function. It will be a hyperplane, but will the hyperplane go through origin? Okay. So I would like to convert this to a linear function. What's a linear function? It goes through the origin. Now, in order to sort of understand how these things work, to simplify our interpretations, it's always much more convenient to work with linear functions. So this was your affine function. So here's what I can do. I can augment the input by a single value of 1. Now the corresponding weight of that input pegged to 1 becomes the bias. And now if I think of the augmented input as the new input, the function suddenly became linear, right? How did I convert something that was an affine to a linear function? What magic happened?
By adding bias.
So, but how? Somebody said something on Zoom? What was that? So here's what happens. This is x1, this is x2, and then I added an x3 whose value was always 1, right? So that means now I'm working entirely within this plane where the x3 value is 1. And in this plane, my boundary doesn't go through the origin. Because on that plane, it's really just affine, right? But then when I look at the augmented input, I can draw a hyperplane which goes through the origin, which slices this plane at the boundary. And so although the intersection of my hyperplane and the x3 equals plane, one plane is a line that doesn't go through origin, the actual decision boundary that I came up with in this augmented space actually goes through origin. That makes sense to everybody, right? And so that's how I convert something that's affine to linear. And now I can work with linear stuff. Now, questions?
Can you explain that again?
Okay. So let's look at this one here, right? In 2 dimensions. This line doesn't go through origin. And I have some pluses here, maybe, and some minuses here. Now, this is a two-dimensional input, x1 and x2. Suppose I add an x3 equals 1 as my input. So then, now this is x1, this is x2, this is x3, and x3 is always pegged to 1, right? So that means all of my data lie on this plane where x3 equals 1. And on this plane, I have pluses and minuses. And that's basically just taking this entire plane and lifting it to x3 equals 1, right? So that decision boundary is going to be something like this. That doesn't go through origin. But I can draw any line over here and draw a plane through that line that does go through the origin over here. And so by adding this x3 component whose value is 1 and lifting the plane off the, lifting the plane up, I put myself in a situation where I could actually draw a new plane that went through origin. I converted the problem to linear. And so now I can work with linear functions, right? Now, here's the thing. So I'm going to speak of linear functions. I'm speaking, we want to find a function, a set of weights wi. Sorry. Right. So we want to find a set of weights wi such that summation wi xi equals 0 represents the equation for a hyperplane that cleanly separates the positives from the negatives. Now, I can write it somewhat differently. I can write all of the, when I say summation wi xi, this is the same as this is showing it in explicit scalar form, but then I can write all the wi's in vector form, which is w1, w2, wd. I can write all the x's also in vector form, x1 through xd. So what if I write it like this, what is the summation term? It's the inner product between w and x, right? So this is simply going to be, this term is w transpose x. If I equate it to 0, the boundary is w transpose x equals 0. Yeah?
What's the benefit of working with linear functions instead of affine?
We will get to this, right? I can write things in this manner, w transpose x equals 0. That's my boundary. Now, when I tell you w transpose x equals 0, what's the relationship between w and x? If the inner product between two vectors is 0, what is the relationship between the two? They're orthogonal, correct? So now we have this, if this is the boundary, then clearly this, for any w, this is my w. This represents the set of all x's that are, how are they related to w? Orthogonal to x, w. So this is going to be this hyperplane of all, going through the origin of all vectors that are orthogonal to w. Make sense? Right. Now, if I have a vector on this side of the plane, the same side as w, I have some vector here. What will the sign of w transpose x be? Anyone?
Yeah.
What is the inner product of two vectors?
How much can the same directions?
It's going to be the length of the first vector times the length of the second vector times cos theta, right? What is theta over here? Is it greater than 90 degrees or less than 90 degrees over here? Over here. What is that? What is theta? So what will w transpose x be? Positive, right? If I have some x on this side, let me call this, say, x prime on this side. In this case, what will w transpose x be? Guys, negative, because theta is greater than 90 degrees, right? So I can simply run a test. If W transpose X is greater than 0, that represents this portion of the space. That's class 1. If W transpose X is negative, that's class 2, right? That makes sense to everybody? That's the first concept. And so I can just write it like so. W transpose X equals 0 is the hyperplane comprising all X's orthogonal to W. And everything that's in the same direction as W is going to result in a positive inner product. Everything that's on the other side of W is going to result in a negative inner product. Everybody with me? Right. So now let's also look at one more question before we proceed. So let's say I have a positive instance of X. So I have some input and I have some X. I can draw various decision boundaries that keep X on the positive side, right? This would be a decision boundary that keeps X on the positive side. So this is my X. This could be another decision boundary that keeps X on the positive side. There are a whole lot of decision boundaries that keeps X on the positive side. Which decision boundary keeps X the farthest from it? Which one does? Somebody said it. Could you repeat that? So of all of the various decision boundaries that I can draw, the one that is at 90 degrees to it is going to be the farthest from it, right? Because for anything else, this distance is going to be smaller, right? That makes sense to everybody? So in other words, for any given X, what is the optimal weight vector if X is a positive instance? Anybody? Come on, guys, you just answered me already.
W dot X equals to 0.
Pardon me?
W dot product with X equals to 0.
We want it to be positive, right? So here's, if I have any given X, if I have any X, the optimal decision boundary is at 90 degrees to it, correct? So what is the weight vector? Come on, wake up, guys. Rishikesh, what's the weight vector? What is the yeah?
The orthogonal line to X.
The orthogonal is this. If this were the weight vector, then what would the decision boundary be? If this were the weight vector, what would the decision boundary be? This one, right? Is that a good one? No, right? You agree with me? So if you want the decision boundary to be as far away from X as possible, you want it to be orthogonal to X. What is the weight vector that results in that boundary? X itself, right? For any positive instance, the best possible weight vector for the decision boundary is going to be X. Can you say it aloud? X? Oh, okay, thank you. If X belongs to the negative class, what is the best weight vector? Can you say that aloud? Guys, can you say minus X? Thank you, right. So basic idea, if I have a positive instance, X meaning, if I have an X and this X belongs to the positive class, then I want the weight vector also to be the same as X, because then that gives me this decision boundary, right? On the other hand, if I have a negative instance, so over here, again, I have X, but X belongs to the negative class, this is X, then I want the weight vector to point exactly opposite to X. That will still give me this decision boundary and keeps X as far away from from the boundary as possible, but now the inner product is going to be negative, right? That clear to everybody? This is the basic principle that the perceptron learning rule is built on. So here's how it goes, right? I'm given just this collection of dots, and I want to find the decision boundary that cleanly separates the red and the blue dots, and I'm going to assume that the red and the blue dots can be separated by a hyperplane. In other words, they are linearly separable, right? So I want to find the W such that W transpose X is positive for all the red dots and negative for all the blue dots. There's a closed form solution to it, but the popular solution originally proposed by Rosenblatt is an online algorithm, which is the famous perceptron algorithm. You initialize W any odd how, and then keep incrementally correcting it until classification errors are minimized. How so? We know that for any positive instance X, the optimal weight vector is X itself, with maybe some scaling. For any negative instance, the optimal vector is minus X. So you start off with some W. You begin classifying all of your training samples. If you encounter a positive instance that is misclassified, then you drag the weight vector towards the optimal weight vector for that positive instance. You drag it towards X. And you do this by simply adding X to W. If you get any negative instance that's misclassified, then you drag the weight vector towards the optimal weight vector for that X, which is to say you drag it towards minus X. You subtract X from W. Make sense? Right? And so here's how here's the perceptron learning algorithm. You're given some collection of training samples. I'm using a +1 and -1 representation for arithmetic notation, but the pictorial illustration should be clear enough. You initialize W, and then you cycle through the training instances. Skip the arithmetic. Here's what it looks like. I'd have a collection of positive and negative instances. I initialize my W, that gives me some decision boundary. I begin checking all of my training instances. And eventually, I'm going to find a misclassified training instance. For this misclassified training instance, what is the optimal weight vector for just this guy? It's going to be that way, right? And so I'm just going to add that to the current weight vector, and that gives me a new weight vector and a new decision boundary, right? Now I check all of my training instances again. And now maybe I find a positive instance that's misclassified. It's on the wrong side of the boundary. What is the optimal weight vector for this positive instance? It's going to be that vector itself. So I just add it to the weight vector. I get a new vector. I get a boundary. And voila, I have a perfect decision boundary. So long as the data can be separated by a linear boundary, this algorithm is guaranteed to converge in a finite number of steps. It will not cycle. So if the classes are linearly separable, it's guaranteed to converge in a finite number of steps. There's a very nice little proof. We'll have the proof up as extra reading on the website if you're interested. But here's the situation. If the classes are not linearly separable, for example, if I have a red dot on the blue side or a blue dot on the red side, will this ever converge? Yes or no? Why not? There's always going to be an instance that's misclassified. You're going to be chasing that tail all the time, right? So this will not converge. The perceptron algorithm will not converge. And so here, this is what we have when we have a very simple problem of just one perceptron. Now, even if I assume that the data are linearly separable, if the data are linearly separable, I know I can find a boundary, but I have to search a bit. Now let's go to something more complex, like this double pentagon problem. In the double pentagon problem, I know that with that architecture to the left, I can construct a network that exactly classifies this double pentagon boundary. We've seen this in past classes. And the way it would do it is that each of these perceptrons in the lower layer is going to capture one of the boundaries of one of the pentagons. The next layer, one perceptron is going to capture one pentagon, the other is going to capture the second one, and then you OR the two, and so you get the desired decision boundary. Except that when you're trying to train this, you'll just be given these dots, right? You're just going to be given these dots. You have to learn the boundary. Now, can I apply the perceptron rule that we just saw to learn these boundaries? To make this more obvious, let's just assume that some oracle, I just got this collection of red and blue dots. And then some oracle came along and told me what the remaining 9 perceptron the weights for the remaining 9 perceptrons in that layer are. So I'm only left with the problem of learning the weights for the 10th perceptron, which I've shown encircled. Can I, and the training data I have, of course, are these, right? The red and the blue dots. Can I learn that perceptron from this data? Everything else is given. The entire network is given. But the oracle just failed to give me 1 perceptron. Can I learn that perceptron from this data? Yes or no? Yes. Can I? Who says yes? Raise your hand. Who says no? And why are you guys undecided? You at the back. Yes or no? You at the back. Do you think it can be determined from just this data? Yes or no? No. No? Okay, why not? What was the requirement for us to be able to learn a perceptron? The data had to be linearly separable. Are the classes linearly separable over here?
But we don't know the weights of the other.
You know the weights of all of the other perceptrons.
Then we can make those specific boundaries, and then it can become a linearly.
Is it? How do you know, right? You can draw all the other boundaries. But if you want to learn this thing, what would you have to do?
Maybe add another dimension.
Pardon me?
Add it another dimension.
That still doesn't help. Does that make this classes linearly separable? Yeah, what would you do?
Is there a way to use the information from the perceptrons to transform the data and then make it linearly separable?
How would you do that? I'm giving you a very simple example, right? Anyone?
Make it a quadratic function.
So, yes.
You can introduce some nonlinearity to.
This is what my network is, right? This is very trivial. So here is what I would need to do. If I want to learn this perceptron, I'm going to have to relabel some of those blues so that the 2 classes now become linearly separable. And then and only then can I learn the perceptron. There's no other way for me to learn the perceptron. Which instances do I relabel?
Which have been classified.
How do you know? Remember that if you mislabel one instance, the entire network is off. How would you know, right? So here's a poll, and then we'll get back to that question.
Doctor, what poll is this?
30 seconds. Give me another 30. Okay, guys done? What's the answer to the first question? Okay, the first statement and the second question. Is it true or false? And the second one? Right, so given the data shown on slide, well, that's not 60, 68, and given that all but the 1 neuron highlighted in yellow are already correctly learned, you cannot learn the perceptron, you cannot use the perceptron learning algorithm to learn the 1 remaining perceptron. It's not possible. And the reason is perceptron learning requires linearly separable classes, but the data are not linearly separable. And so if you really want to learn the perceptron rule, here's what you're going to have to do. You're going to have to begin relabeling some of the instances and then learn the boundary. And the correct solution for you is that you don't know which label to instances to relabel. So you're going to have to check. You know that there's a perfect that perfect classification is possible. So you relabel the data instances in every possible way and try to learn a decision boundary until you find a relabeling that gives you a decision boundary, that gives you the perfect classification for the entire training data. Does that make sense? Right, so the individual classifier, so this labeling will not work. The individual classifier will need this kind of labeling, which is not given. And so we actually have to figure out how to relabel the data in order to learn this classifier. And this business of figuring out how to relabel the data is combinatorial. If I have n training points, I need to look at every every one of the 2 raised to n minus 1 possible ways of relabeling the data, because some blues may have to be relabeled to red, some reds may have to be relabeled to blue, and then you learn the boundary, and then you check on the entire training data whether the final classification output is correct or not. And that's a combinatorial problem. And so for a single line, we have to try out every possible way of relabeling the blue dots such that we can learn a line that keeps all the red dots on one side. And that's when I've given you the entire network. If I start off, tabula rasa, no neuron is known. I've given you the correct architecture. Here's what you would have to do. You would have to look at every possible way of relabeling the data for every one of the neurons in your network, such that when you learn the boundaries for each of the neurons, the resulting output of the network is perfect. And this is a combinatorial search. You're not going to do it in any reasonable amount of time. It's not going to work. And so for even this very simple double pentagon problem, we must know the desired output of every neuron for every training instance, basically how to label them. And we have to do this such that when you combine them all, the overall decision boundary is the double pentagon. This is a combinatorial optimization problem. And if you make a mistake on just one training instance, when you relabel, your entire classifier is going to be junk. And so this is the problem. Training this network using the perceptron rule is a combinatorial optimization problem. We don't know the outputs of the individual neurons for every one of the training instances. We need to relabel them and search through the space. So we must also determine the correct output for each neuron in every training instance, which is at least exponential in the size of the inputs. And so this is not a feasible solution. And so this actually sort of froze research into multilayer perceptrons for a very long time. People realized that, the original perceptron and MLP were based on the simple linear classifiers and the threshold activation. And very soon people realized that the problem of learning an individual perceptron may be tractable, but if you want to learn an entire network, you run into this combinatorial optimization problem that cannot be solved. And so a variety of greedy solutions were proposed, like Adeline and Madeline and a bunch of others, Bernie Widrow, who's still a prof in Stanford, and who once stole a couple of my students. But anyway, I haven't forgiven him. These were what persisted for almost 3 decades before Paul Verbos, in MIT figured out that there was an alternate way. That was in the early 70s. And there was another gap of 15 years before Jeff Hinton saw the value in Verbos's thesis from 15 years ago. So what is the solution? For that first, here's the story so far. Learning a network is the problem of learning weights and biases to compute a target function, assuming the network has sufficient capacity. In practice, we learn networks by fitting them to match the input-output relationship of training instances drawn from the target function. A linear decision boundary can be learned by a single perceptron in linear time, really. If the classes are linearly separable, for nonlinear decision boundaries, we need networks of perceptrons, but training an MLP with threshold function activation will require the knowledge of the input-output relationship for every training instance for every perceptron in the network. And these must be determined as part of the training. And for threshold activations, this is an NP problem. It has NP complexity. So the realization that training an entire MLP was a combinatorial optimization problem stalled the development of neural networks for well over a decade until we had this little insight. And what is that? Here's the problem. What we are really trying to count is the error. How frequently is the network correct? How frequently is it wrong? We have a bunch of training inputs, and the output must be either 0 or 1 for these training inputs. Then at each of these inputs, you can compute the output of the network, and the output of the network may be either right or wrong. And we are counting the number of misclassifications it makes, and then we try to set the parameters. But now let's say I have these training data, x1 through x5, and the dotted line is obviously the correct decision boundary. Let's say I have chosen or built my network so that it learns the green, it represents the green function. So the green function is going from 0 to 1 at some point. It's making 2 errors. Now, if I move this threshold where it moves from 0 to 1 left by a little, will the number of errors change? If I move it right by just a little, will the number of errors change? I have to move it a whole lot. It has to cross a training point. If I move it just, perturb it just a little bit, the number of errors will not change, right? And that is the actual problem. So same thing over here. If I'm trying to learn a perceptron of this kind in multidimensional space, I may start off with an initial boundary, and it's going to misclassify some instances. If I rotate the boundary a little bit, the total number of errors will not change till the boundary actually crosses a misclassified training point. So little wiggles of my parameters will not result in any change of the error. And that's why we really can't optimize things using incremental steps. There's no indication of whether I should rotate the weight in this direction or this direction, because a little bit of rotation this way or this way doesn't really change the error. And when you go to more complex problems like this, it gets even more complicated. You can change the parameters of the individual neurons quite a lot without changing the overall error. And so you won't even know if the changes that you're making are going in the correct direction or not. So this makes it really challenging. In other words, if I were using threshold activations, the MLP is a function which has 0 derivative almost everywhere, because I can change the parameters a whole lot and the error doesn't change. And then whenever the boundary crosses a misclassified point, the error changes a lot. And so you have a small number of points where the derivative is infinity and other points where the derivative is 0. So this is basically a very ugly function to work with no derivatives where it's interesting. So given this, how would we change the problem? Here's what we're going to do. We're going to change our way of computing the mismatch such that modifying the classifier slightly lets us know if you're going in the right direction or not. So here again, if I move the green threshold left or right, it doesn't tell me if my errors are decreasing. So I could move the green threshold a whole lot to the left, and the error would not change. So it doesn't tell me that this is the wrong direction to be going, and I could keep going that way, right? So we're going to change 2 things. We're going to change the activation function. Instead of being a threshold, we're going to make it vary smoothly. And we are going to change the manner in which we count error. So here are the 2 things we do. We are not going to use a threshold activation anymore. We are going to use an activation function that varies smoothly, which could be a sigmoid, typically if you're performing classification. But inside the network, you could have other kinds of activations. And the neuron is going to be differentiable with non-zero derivatives over much of the input space. Now, having a non-zero derivative means that you know how much a small perturbation of the input will perturb the output. And this enables us to, you will know how a small perturbation of a weight will perturb the output. And this enables us to estimate the parameters using gradient descent. And the other thing we're going to do is to change the manner in which you count the error. So to go back to our illustration, over here, if these were my training data, the red and blue dots were my training data, and if the current network was this dotted line over here, at threshold T1, if I move the threshold all the way back to T2, the total error is not going to change. So this doesn't tell me that moving the threshold from T1 to T2 is a good thing to do. Instead, we are going to change the activation function to something of this kind. It's not a threshold anymore. In this case, it's a sigmoid, which goes smoothly from 0 to 1, number 1. And here, you can classify the output as a 1 whenever the function is above 0.5, and 0 when it's below 0.5. So you're still performing classification. The second thing we're going to do is that instead of simply counting the number of misclassifications, we're going to replace that by the distance from between the target output and the actual function. So instead of simply counting misclassification errors, we are going to take the total length of the dotted lines, which is the distance between the target output and the actual function. And when I do this, then you can see that if I slide this function leftwards, like so, then the total length of the dotted lines actually decreases. And so this gives me an indication that moving left is a good thing to do. But observe that this is not really the problem that we're trying to solve. What is the problem we're actually trying to solve?
Number of misclassifications.
We want to minimize the number of misclassifications. This is a proxy. Will minimizing this proxy necessarily also minimize the number of errors? Not necessarily. Can you give me an example of how that would happen or not? Yes.
So if you move to the left, there are certain points at the blue which will, like, their length will increase from the function. So they will be showing the error.
So I'm not sure if this is what you mean, but consider this example, right? Here, when I begin misclassifying, counting the total distance. So let's say I have, this is my data, and I have my class zeros out here and class ones out here. And let's say I have a whole bunch of these, 1 million of these guys or 1 billion of these guys out here, right? Each of them is going to have a very minuscule distance from the curve. But cumulatively, the distance is going to be a lot. So these guys over here, just in order to minimize the distance between these points on the curve. So if I plot my curve like so, the curve never really goes to 1. There's always a small distance. And if I have a very large number of positives out here, these things will want the curve to be closer to 1. And how do they make the curve closer to 1? They're going to push the curve out this way, which will end up in misclassification of the blue dots. That make sense? So you're very sensitive. So we are working with proxies. And proxies, optimizing this proxy is no guarantee that the actual function that you're trying to solve will be solved. Nevertheless, we're going to have to work with proxies because working with the actual function results in a combinatorial problem that cannot be solved. That makes sense to everybody? Questions? No. It doesn't matter so long as the distance is not, the moment the distance becomes 0, you have a 0 derivative, which kills you. If you have a non-zero derivative, you'll always have this issue. Okay, there's a point. I will give you 2 minutes for this poll because there are many options. 90 seconds. Okay, time's up, guys, but I can give you another 10 seconds. All right. Anybody want to answer this? Evgeny. The first statement of the first question, is this true?
Yes.
What about the second one?
Yes.
Third? Fourth?
Yes. No.
There was no fourth. Okay. How can you say yes? Okay. In the second question, is the first statement true?
No. No.
Second one? And the third? Okay. So for the second one, the crossover point was 0.5. Until the 0.5 point actually crosses a misclassified point, the actual count of errors will not change. But what will change is your proxy, which is the total distance. So that actually remains true, right? And so here's what we have. Increasing or decreasing a threshold will not change the overall classification error unless the threshold moves past a misclassified point. And you cannot know if a change moves it in the correct direction that will eventually result in overall decrease in the error. And so there's no derivative. The derivative is either 0 or infinity. The derivatives don't give you any information. Whereas if I use a sigmoid activation, firstly, misclassifications, the actual count of errors will only change when the 0.5 point goes past a misclassified instance. Nevertheless, the total distance of the value of the function from its target value will change as you move the function left and right. And this gives you a non-zero derivative. If I look at this total distance, this has a non-zero derivative with respect to perturbation of the parameters. And that helps us figure out how to change things. So the two key requirements for learnability are, firstly, the activation must be continuously varying. It must be differentiable. And secondly, the error function must also be continuously varying. A small change in your activation in the function must result in a measurable change in the error. Otherwise, you can't really know which way to go. That make sense to everybody? Yeah. Okay. And so let's look at continuous varying activations. You have, obviously, you can't be using a threshold activation. It has zero derivative or infinite derivative. So we need one of the other kinds. We like using sigmoids. We want activations that are differentiable, that are continuous and differentiable almost everywhere. I say almost everywhere because this function, the red curve, is not differentiable at x equals 0. Nonetheless, it has something called a subderivative, which gives me some kind of a bound on the derivative, which we will see in the next class. And so you still get some notion of which way to perturb the parameters. And so you want activations to be differentiable everywhere. And one specific activation that's particularly interesting is the sigmoid. The sigmoid is 1 over 1 plus e raised to minus z. Now, if z is a very large negative number, if z is minus infinity, what does this become? E raised to minus z is e raised to infinity, which is infinite. 1 over infinity is 0, so this becomes 0 for when z is a large negative number. When z is a large positive number, e raised to minus infinity is 0, so it's 1 over 1, this becomes 1, right? And so this function is 0 for very large negative inputs. It's 1 for very large positive inputs, and in between, it varies smoothly. It gives you the sigmoid. And the sigmoid, so, has a very nice interpretation. Where did I keep my chalk here? So just to go over that, if I say, just to write it down, if I have 1 over 1 plus e raised to minus z, for z equals minus infinity, that's way out to the far end, this is 1 over 1 plus e raised to minus of minus infinity, which is 1 over 1 plus e raised to infinity, which is what? 1 over infinity, which is 0, right? And if z goes to plus infinity, This is 1 over 1 plus e raised to minus infinity, which is 1 over 1 plus 0, which is 1. So, and in between it varies continuously. Now this has a very nice interpretation. How the interpretation is arrived at is on the slide, so please take a look. Which it can be interpreted as the a posteriori probability that the class takes the value 1 given the input. We will revisit this topic in a lecture several weeks from now, but if you want a quick sneak peek, take a look at the slides. And so we'll return to the fact that perceptrons with sigmoid activations actually model class probabilities in a later lecture, but for now moving on, here's what we have. The perceptron's activation is differentiable. The error that we computed is also differentiable. What does it mean for something to be differentiable? When I say something is differentiable, here's what we're speaking of. We are saying that if I say, if y is a function of x, then I'm saying that dy over dx is defined. It has a value that I can know. And it can take a value 0, but we don't like 0. So when we speak of differentiable, we are speaking of functions that not only have measurable dy over dx. In our context, that this dy over dx is a non-zero value. That's in our context, right? So let's say this is some value c, some value whatever. Let me call this a, which means that it tells me how much a small perturbation of x will result in a change y. I get this dy equals a times dx. So for a function when a function is differentiable, it tells me how much a small perturbation of any input to the function will perturb the output. Now in this case, our inputs are a weighted combination of x's and w's. So this means that if the activation is differentiable, it will tell me how much a small perturbation of the weight, of the incoming weight, will result in a change in the output of the function. Right, exactly. And so this means that if I have a perceptron of this kind, if sigma is differentiable, then I'll get some idea of how changing this w a little bit will change y. And subsequently, when I have the chain rule over here, we'll get back into it, go into it in a little more detail later. But what this means is that because the function is differentiable, I'm able to quantify how much a perturbation of w will perturb y, which means in this network, I will be able to quantify how much a small perturbation of this w is going to perturb the output of this guy. I'm also going to be able to quantify how much a small perturbation of this guy will perturb this output, and how much a small perturbation of this guy will perturb this output. And because the subsequent activation is also differentiable, I will be able to tell you how much small perturbations of these guys are going to change y. And so if I chain them all together, I can tell you how much a small perturbation of this one w is going to change the y at the very end of the network. And so I will be able to tell you that increasing this w a little bit will increase y, or decreasing it will increase y. This information is something that I can compute. And that's not just one weight. That means the entire function is differentiable. I can tell you exactly how changing any individual parameter of the network is going to change the output. So at f of x semicolon w is now differentiable with respect to every element of w. And exactly how these derivatives are obtained, we will see later. The second one is the continuously varying error function. This must also be differentiable. Why so, right? Because you want to have the error between y, and it's not enough to say that perturbing this w perturbs y. We need to be able to compute how much perturbing this w perturbs the error. And so you want the error to be differentiable. Now, given all of these, this is how we're going to define our error function. We define it in terms of a divergence function. Our divergence function has these properties. It takes two inputs, in this case f and g, And the divergence will be 0 only when f equals g. When f doesn't equal g, then the divergence is going to be positive. Regardless of whether x is greater than g or less than g, if the two are not the same, the divergence will always be positive. And finally, of course, we're going to define our divergence function so that it's differentiable with respect to f, so that we can chain things together to compute how much changing an individual parameter changes the overall divergence. This divergence quantity, yeah.
There's a question from Zoom. Can the type of data I'm dealing with primarily help me make a good choice of activation function or some statistical properties from the data at least?
So take a look at lecture 2 for what is a good activation function. We'll deal with this later in the course too, right? Now, so the divergence function quantifies the mismatch between the network output and the target output. And for classification, this is typically not the error, but a proxy, right? So how does this look? When your function f, your network, has the capacity to represent x, this error is now a divergence function, and the shaded area is simply going to be the integral of the divergence function. But then we make one more small change. And the change is, you don't need to minimize the shaded area everywhere. Let's say you know a priori that x can never take extreme values. Then do you really need to consider the error in those regions? You don't, right? You only need to consider the error at the x values that are actually likely to happen. Or more generally, what we want to do is to weight the divergence at any x with the probability of that x. So the more probable a specific x is, the more probable, more frequent a particular input happens, frequently a particular input happens, the more importance you want to give the divergence at that input. And so the actual objective that we will try to minimize is this guy, which is the integral over the input of the product of the divergence between the output of the network and the desired output of the network at that x, multiplied by the probability of the x itself, integrated over all of x. This is the expected value of the divergence. For those of you who know your statistics, this is the statistical average of the divergence over the entire input space. And so what we really want to do is to minimize the W, optimize the W to minimize this expected divergence. But then once again, we have the issue that we don't really know G. We only know, we're only able to collect some samples of G, some input-output pairs. And so rather than minimizing the expected value of the divergence over the entire input space, we are going to minimize the average divergence over all of your training samples. But then something magical happens when you collect training samples. When you collect training samples from a natural process in a natural manner, then you're naturally going to get more samples from more probable regions of the space and fewer samples from less probable regions of the space. And so this empirical estimate for the expected divergence naturally gives more importance to more frequent x's and less importance to less frequent x's. And so this is what we will actually be minimizing. This is what we call our loss. Our loss is the empirical estimate of the expected divergence between the output of the network and the desired output of the network. It's our empirical risk. For a given collection of inputs x is given. So the only thing that can be changed is W. And so this loss function is actually going to be a function of W. And we will be finding the W that minimizes this loss. So this becomes a problem of function. Again, the empirical risk is only an empirical approximation to the true risk, which is the expected divergence. Keep that in mind, right? And so this is the overall problem statement we end up with. You're given a collection of input-output training pairs, and you compute the average divergence over the entire training set, which is your loss. And you minimize this with respect to W. This is a problem of function minimization. We will go over this in the next class. I'm behind, so the summary is on the last slide. Please go over it. Thank you. I'll see you in the next class. Yes. Let's talk outside. Let's talk outside.
That's okay. Just all